Alrighty, hello Geometry B. We're back for another video. Today what we're going to do is we're going to talk about quadrilaterals and this thing called coordinate proof. Right, so what the heck is a coordinate proof? They're not quite the same as the proofs that you've done in the past. Coordinate proofs is when we're using coordinates in a graph system, right? Like we're just literally plotting them on some axes, like an x and a y. And then we're going to use that and prove some properties of the different figures. So we are going to cut this unit down a little bit because we're all learning at a distance, right? So what we're going to focus on mostly is this slope formula. So it's the same slope formula that you've hopefully seen many, many times before. We've got m, that's the variable we use to represent slope, and the slope is equal to y2 minus y1 over x2 minus x1. So you might also be asking yourself, like, what the heck, where do those x1s and y2s come from? So what happens is that they come from 2 points. Right, so when you're working through problems with these, you're going to have a set of points that you're trying to find the slope between. Right, so one of those points is going to be x1, y1, and the other one's x2, y2. Right, so we're going to take a look at, just calculating the slope, right, going with the bare bones of all this. Again, hopefully something you guys have done in the past. But the important part is that your x1 and y1 are from the same point. Your x2 and y2 are from the same point. You don't want to mix and match those. Right? After that, all it is just plugging it into the slope formula where it asks for them. The tricky part that people sometimes make mistakes on is that there is subtraction that's built into this formula. Right? We're going to take a look at what that means and where we have to be careful for that. Right? So to calculate the slope between these 2 points, right, first thing I'm going to do is I'm just going to label the points. Right? I'm going to call this one x1, y1 because it's the first one on there. I'm going to call the other one x2, y2. And all I need to do is use that same formula, right? We have the slope is equal to, up top we're going to have the y2, which is 20, minus the y1, which is 5. Cool, no problem. On the bottom we've got the x2 minus the x1, which is negative 3. So this is that part I was just talking about a second ago, where we got to be careful that there's this subtraction that's built into the formula, and then we have that negative 3 after it. And so whenever you have that double negative, what we want to do is we want to turn it into a plus. Right, so whenever you have, like, in this case, 7 minus negative 3, that's really 7 plus 3 in disguise. Right, after that, it's just as simple as kind of doing out the subtraction or addition. Right, 20 minus 5 is going to give us 15. On the bottom, 7 plus 3 is 10. We get 15 over 10. Now, technically, there's nothing wrong with leaving it like that. But if you remember the last time you ran into slope and we talked about it as rise over run, right? You would have to rise 15 spots and then go over 10 spots to like graph anything with that. That's quite a bit of space to cover on a graph, right? So what we really want to do whenever possible is reduce that fraction down. Right? So if I have 15 over 10, that's the same thing as 3 over 2. Right? You can divide both of those by 5 and kind of reduce it that way. So overall, our slope between those is 3 over 2. Cool, nothing to it. Right. Let's take a look at this second one here. Right. Again, same deal. I'm going to just label my points. x1, y1, x2, y2. Now you don't have to do that every single time. Right? If you're feeling super duper confident on things, you could skip the labeling step, but to be fair, I still do it, and I've been doing this a long time. Right. So it's never a bad idea. Something you might also notice me doing is that I'm writing out like m equals, and then I have like this little kind of skeleton thing over here. Right, I've got the top and bottom of a fraction, and I already put my subtraction in there. Right, the reason I'm doing that is because I find that it helps me, not make that mistake like we sort of talked about over here, right? I need to make sure I have minus any negatives. Right, so if I include that subtraction right from the start, less of a chance I'm going to make that mistake. Right, so up top we got y2, which is 7, minus the y1, which was 6. On the bottom we've got x2 minus x1, so negative 1 and 4. So in this case, we didn't have to worry about any like double negatives, right? We didn't have to worry about, oh, subtract this negative number, right? We are subtracting with a negative 1 on the bottom, but they're not like next to each other, right? It's not, negative 4, right? So we don't need to change anything. Right, so up top, what we're going to have is 7 minus 6 is 1. On the bottom, negative 1. Take away 4 more is negative 5. And 1 over negative 5 is technically fine. But you might be thinking to yourself, like, wow, that looks a little weird, and I don't know why. So most of the time, we don't have negatives on the bottoms of fractions, right? So what we can do is that 1 over negative 5 is the same thing as just negative 1/5, or it's also the same thing as negative 1 over 5, right? All three of those mean the same thing. What we're going to want to do is we're going to want to choose to use either this one or this one, right? Those are normally the ways you see it. You don't normally have subtraction on the bottom of a fraction, right? So either one of these, again, they mean the same thing. Either one of those is perfectly fine as our answer for the slope between those 2 points, right? So hopefully pretty easy review of slope formula, nothing too fancy. And there's a couple things that we can tell from slopes. So you're going to want to be trying to remember back to geometry A, right, whenever that was for you. And depending on the relationship between the slopes, we can tell certain things about the lines they represent. So if we know that the slopes are equal to each other, right, like say that both of these came out to 3 over 2, then we would say that those lines are parallel. If they're opposite reciprocals, then that means that the lines are perpendicular. All right, so just remember that parallel means that they're traveling in the exact same direction. They never intersect, right? They don't have any points of intersection. They're never going to meet. When we're perpendicular, we are crossing each other, but we're crossing the lines very specifically with a 90-degree angle. So you might be asking yourself, like, what the heck is an opposite reciprocal? I don't remember that too much. Right? It sounds a little familiar, hopefully, but opposite reciprocals is just what we're talking about. Say, we were just talking about 3 over 2 as a slope. The opposite reciprocal, right, the opposite reciprocal of 3 over 2 would be negative 2/3. Right? So reciprocal just means that we're basically flipping the fraction. Right? So if I had, if this was 7 over 2, the opposite reciprocal would be negative 2 over 7. Right? So the fraction is getting flipped, and then the opposite part is changing the sign. Right? So this was a positive 7 over 2. All of a sudden, we flipped it, changed it to a negative, so it's negative 2 over 7. Right? Sometimes, depending on what our original slope is, it can be a little tricky to figure stuff out. Let's say our original slope was just negative 3. Uh-oh, it's not a fraction. How am I supposed to flip that? Oh no, what do we do? Don't forget, whenever you have a whole number, it's just that number over 1. Right? Negative 3 and negative 3 divided by 1 are the same thing. All right, so then if I wanted to take the opposite reciprocal of that, right, what I would do is I would flip it and change it to 1/3. And then because it was negative, now this is positive. Right? In all honesty, I don't really need that plus sign there. Right? So we would just say that the opposite reciprocal is 1/3. Right? So if we have slopes that are opposite reciprocals, they are perpendicular lines. Right? They intersect specifically at a 90-degree angle. They're perpendicular. Right? So let's get into the actual coordinate proving piece. Right, so there are a couple different ways we can prove that a quadrilateral is a parallelogram using this coordinate proof stuff. All right, so you're welcome to read through all of these, but what I'm going to tell you is because we're kind of paring this down, there's a couple that we're not going to worry about. All right, so this one way up at the top, show both pairs of opposite sides are parallel using slopes. Ding, that's exactly what we're going to do. Right? You could also show that the diagonals bisect using midpoints, but we're not going to talk about midpoints. Right? It is an option, if you know the midpoint formula or if you want to look it up, that is something you could do. We're not going to talk about it too much. You could also show both pairs of opposite sides are congruent using distances. Again, we're not really going to go into the distance formula right quite yet. Last but not least, we could show that one pair of opposite sides are parallel and also congruent using distances. Right? But again, we got that one first method up there where we can use the slopes. That's what we're going to focus mainly on. Right? Again, if you want to investigate some of those other ones, send an email, send a quick G-chat, something, and we can talk through it. But we're only going to focus on the slope part. So for this example here, I've got some points. I've already got them graphed because I didn't trust myself to do it while I was recording. So So we're going to prove if this quadrilateral with these coordinates is a parallelogram. All right, so we got C, O, B, and S. All right, so COBS. That's such a weird name. I don't know if I've ever heard that. So what we're going to do is we're going to try and prove that the opposite sides are parallel. All right, so if I'm taking a look at the opposite sides, say I'm taking the side from C to O, right? If I'm doing CO, that's opposite from SB, right? Those are ones that I'm going to want to have the same slope, right? The other pair of opposite sides is going to be OB and SC, right? So those ones we're going to want to match up, right? So all we're going to do is we're going to use our slope formula and calculate these different slopes, right? So from C to O, it's pretty easy. We got our points right above it. That's pretty handy. So what we're going to do is for CO, I'm going to just go ahead and take these points. Right? I can call this one x1, y1. I could call this x2, y2. And I'm just going ahead and plugging them in the same way we did up top. All right, so I'll have that the slope is equal to, we'll do y2, which is 3, minus y1, which is 5. On the bottom, we'll do x2 minus x1. Right, so from C to O, we can do 3 minus 5 up top, which is negative 2. 6 minus 1 is 5. Right, so that's our slope from C to O, is negative 2 over 5. Okay. So what we want to do is we then want to check and make sure that that works out with SB. Right. So for SB, I'm going to do the same thing. Right, I'm going to set up my slope formula, put out this little skeleton here, and then now I'm looking at these 2 points. Right, so I'm going to call one of them x1, y1, call the other one x2 and y2. Right, and I'm just going to throw them in right where the formula asks for it. Right, so I've got y2 minus y1. Right, again, we got that double negative thing that we got to be careful on with these. On the bottom, we have x2 minus x1. Cool. So up top there, right, that 1 minus negative 1 is now 1 plus 1. So we get 2 there. On the bottom, negative 2 minus 3 more brings us down to negative 5. You might be thinking to yourself like, oh, weird. Those don't look quite the same. But remember, when we have that negative on the bottom, we can kind of move that negative sign wherever we need it to be, right? That's the same as negative 2/5. It's also the same thing as negative 2/5, right? They're all the same thing. All right, so the one that we want it to look like, and the one that we can make it look like, is the same one we had from C to O. Right? So what we have here is that negative 2/5 is the same thing as negative 2/5. So these are parallel. All right, that's what we're looking for, is we want those slopes to come out the same to show that those opposite sides are parallel to each other. All right. I'm going to go ahead and I'm going to go through the same thing for OB and SC. All right, so for OB, all right, same deal. I'm going to set up my slope formula, making that little skeleton first. And then I'm going to take these 2 points, right, an x1, y1, and the x2, y2. All right. So up on the top, we've got y2 minus y1. On the bottom, we've got x2 minus x1. Up top, negative 1 minus 3 is negative 4. On the bottom, 3 minus 6 is negative 3. And when we have 2 negatives in a fraction, right, remember that fractions are just division. If you divide a negative by a negative, it all comes out positive. So you can actually turn that into regular old 4/3. Right, so 4/3 is our slope from O to B. Right. We still need to double check, make sure that it's the same thing as what we get from SC. Alrighty, we're back at it. Now that my brain's back and turned on, right, now we're going to figure out the slope from S to C. Right, so again, what I'm going to do is I'm going to start by setting up my slope formula just like we did before. Right, and this time the 2 points that I'm looking at are S and C. Right, so I'm calling this one x1, y1. I'm going to call this other one x2, y2. You might be thinking to yourself, like, well, Mr. Pog, why didn't you set the first one, like this one over here, to be the x1 and y1? In all honesty, it doesn't really matter too much, right? As long as we know how to handle things with these weird negatives in the bottom and all that, we're going to be okay. And so on this one, what I'm going to do is I'm going to do y2 up top minus y1. On the bottom, what we're going to do is x2 minus x1. Right? So on the bottom, we got that double negative thing going on. I'm going to turn that into a plus sign, so it's 1 plus 2 down there. Right? And then all we're going to do is we're just going to go through it. Right? 5 minus 1 is 4. 1 plus 2 is 3. Would you look at that? 4/3 is what we had before. The slopes are the same, so these two bits are parallel. Ding. So, because we just showed that these two pairs of opposite sides are parallel to each other, that means that we have a parallelogram. Right? That's all we really need to do for these. Right? Let's try another one out. We've got Carl. Right? So there is another way that you can figure out the slope, and it does go quite a bit faster. Right? So it's still really good to be able to use the slope formula and figure them out this way, right? If you have points that are very large and they're hard to graph on whatever graph paper you have, right, you want to be able to do it with those. However, if we can fit everything on a graph, there's a much easier way. Right? So I've been mentioning rise over run a little bit. So let's kind of set things up and then we'll figure out where to go from there. So here, if I want to try and prove that this is a parallelogram, right, if I'm taking a look at the little picture over on the side, I can kind of tell that it doesn't really look great, right? It doesn't really look like a parallelogram, but we need to be able to prove whether it's not, right? So it's more than just like, it doesn't look like it, right? We need to actually go ahead and prove it one way or the other. So in order to do that, I'm going to again grab the opposite sides, right? So I've got from C to A, and the side opposite from that is RL. Right? The other two pairs of opposite sides are from A to R and from L to C. Right? So to figure out these slopes a little bit more easily, what we're going to do is we're going to start out with C to A. Right? So for CA, I've been mentioning slope is the same thing as rise over run. Right? So let's go over to the graph. I'm going to kind of zoom in a little bit and let's take a closer look at from C to A. So getting from C to A, right, you can think about it as the rise over the run. Right? So think about how many spaces up from C I'm going until I get level with A. Right? So I'm going up 1, 2, 3, 4, 5. Right? So my rise is 5. The run, how far I'm going over, is 1, 2, 3. Right? So if I have a rise of 5 and a run of 3, that means that I can say that my slope is 5 over 3. Right? So again, the rise was 5, the run was 3. Cool, there's my slope from C to A. Right? Again, much easier than going through the whole slope formula and that whole shebang. Right? Still good to be able to use the slope formula, but this is a good alternative. Right? So same thing for R to L. We're going to do rise over run. So I'm going to scooch back over to the graph from R to L. Right? So when we're doing this rise over run piece, what I would really suggest is treat your graph as if you're reading it from left to right. Right? So you're going to want to start with the point that's further on the left, which in this case is L, and you're going to want to go to the one that's further to the right, which is R. Right? Actually, that's really cool that it goes from L to R, left to right. I didn't even plan that. Look at me go. Right? So to go from L up to R, my rise is 1, 2, 3, 4, 5, and my run is 1, 2. Right? So my rise and run is 5 over 2. Alright, so, 5 over 2, those are not the same thing, right? One's 5/3, one's 5/2. That's a big nope from us. Right? So honestly, if we're trying to prove whether or not this is a parallelogram, that's enough, right? We know that they're not going to have opposite sides, right? We can actually just leave the problem there. Right? Just to practice a little bit more with the rise and run if you're feeling a little off about it, let's talk about the other pair of sides as well. To go from A to R, let's take a look at that one. Oops, scooch those out of the way. So we go from A to R, right? This time I'm going down, right? So what I'm going to have to do is I'm going to have to think about, right, if I'm going down, that makes sense that it should be a negative. So it's like I'm falling. So I'm going down 1, 2, 3, 4 spots. So I'm going to treat that as a -4 as my rise. For my run, I'm still moving in a positive direction, so that's fine. 1, 2, 3, 4, 5. All right, so my slope from A to R, I went down 4 and over 5. Right? Going from L to C, right? Again, we can kind of treat it as like we're going to go from the point that's further left to the one that's further to the right. So what I really want to do is kind of count from C over to L. Right, so let's kind of zoom in there. To go from C to L, right, I'm going down 1, 2, 3, 4. So that, again, that's a -4. And over 1, 2, 3, 4, 5, 6. Right, so -4 over 6 is my slope there, which we can reduce to be -2/3. Right? So again, we're seeing on this pair of sides as well that they don't quite match. Right? So all in all, this one is not a parallelogram. Right? Nope, not a parallelogram. Sorry, Carl. Carl's had dreams of being a parallelogram since he was about yay high. Right? What a shame. He tried though. He was pretty close, but he's not a parallelogram. All right, cool. So with coordinate proof, we don't have to stop at just parallelograms, right? We can prove any type of quadrilateral that we've talked about so far. So the other ones we're going to focus on are a rhombus and a rectangle. So we got a couple of different ways we can prove that something's a rhombus, right? So one of the ways, and the one that we're going to focus on more, right? Like this is our like check plus one. First, we're going to prove it's a parallelogram, then show the diagonals are perpendicular using slopes. Right? The other way that you can do it is you can show that all the sides are congruent using distances, right? That's a property of a rhombus we know about, is that all the sides are the same length. But we're not really going to talk about distances here, right? So we don't really need to worry about that. So what we've got down here is we've got Jane. We want to figure out if Jane's a rhombus or not. Right? So what we need to do here is we are first going to prove that Jane is a parallelogram. Right? So again, I'm going to take these pairs of opposite sides from J to A and from E to N. Right. Then what I need to do is I need to grab the other pair of opposite sides, from E to J and N to A. Right. So as I'm taking a look at these, right, I'm going to go through these using rise over run just so it's a little bit quicker. I'm going to make this video a little shorter. Right. You are welcome to use the slope formula if that works out better for you. Right. So going from J to A, I'm taking a look over at the graph and I'm noticing that, all right, my slope, I'm rising 0, right? So my rise is 0. My run is 1, 2, 3, 4, 5 over there. Right? So 0 over 5 is the same thing as just 0. From E to N, it looks like it's about the same thing, right? It's 0 over 5, which is just 0. Right? So those are parallel, right? That checks out. That's good that those match. Going from E to J and N to A, you kind of think about it the same way, right? Rise over run. So from E to J, I'm rising 1, 2, 3, 4, and going over 1, 2, 3. All right, so 4 over 3 is my slope there. From N to A, I'm rising 1, 2, 3, 4, and going over 1, 2, 3. So that's also going to have a slope of 4/3. Right? So those ones also match. Cool. So Jane is a parallelogram. Sweet. I bet Carl's jealous. So Jane's a parallelogram, right? So that's all fine and dandy, but now what we need to do is we need to be able to go ahead and tell whether Jane is a rhombus. So what I'm going to need to do is I'm going to need to take a look at the diagonals. So we're taking a look at the diagonals. Right? I'm looking at these pieces that aren't adjacent to each other. Right? So if I'm trying to put in the diagonals there, I've got this one from J to N, and then I've got this one from E to A. Right? And again, what I want to do is I want to prove that those are perpendicular. They sure look like they are, but I need to actually prove it. Right? So over to the side here, try and keep everything on the screen at once, is I'm just going to find the slopes of each of these. Right? So from J to N, I can think about rise over run again. Right? I'm going down 1, 2, 3, 4, and over 2. So down 4 is negative 4, over 2. Negative 4 over 2 is negative 2. Oops, I don't know why that changed colors there. Is negative 2 over 1. Right? I know that you're probably thinking to yourself, like, oh, well, isn't that just negative 2? Yeah, it is. Right? We could rate it as negative 2. But if I want to prove that things are perpendicular, what I really want is I want to show their opposite reciprocals. Right? Kind of like we talked about a little bit earlier. So if I leave things as a fraction, that's a little bit easier to do. Right? So I'm going to also take a look at the other diagonal from E to A. Right? So going from E to A, I'm going up 1, 2, 3, 4. I'm going over 1, 2, 3, 4, 5, 6, 7, 8. Right? So 4 over 8 for my rise and run. Right? 4 over 8 is the same thing as 1/2. So then what we're doing is we are taking a look at those two slopes, right? From J to N was negative 2 over 1. From E to A was up 1 over 2. Right? So those two slopes are opposite reciprocals. Right? If I take negative 2 over 1, I flip it and I change the sign to its opposite, that turns into 1/2. Right? So because these are opposite reciprocals, right, then that means that they are perpendicular. Right? So now what we've done is we've proven that Jane, oops, everything's kind of loading in all at once there. Jane is a parallelogram and the diagonals are perpendicular. Right? So we have proven that Jane is a rhombus. Oops, rhombus. Cool. That's all we need to do to prove it's a rhombus, right? Is just that. Okay. So the other shape I was talking about was a rectangle, right? So again, we got a couple different ways. We're going to focus on just one of them, right? So one way that we can do is we can show the adjacent sides are perpendicular using slopes. Using slopes, that sounds great. That sounds like what we've been doing. After that, right, we could also prove it's a parallelogram, then show the adjacent sides are perpendicular using slopes. But you might notice that this whole second part of this, show adjacent sides are perpendicular using slopes, that's the exact same thing as the first one. Right? So if you wanted to do a little bit of extra work, you could show it's a parallelogram first. Right? But what we can do is we can just show that the adjacent sides are perpendicular using the slopes. Right? So it's kind of built in to this first one. Right? We could still go through the whole thing, prove it's a parallelogram, and go through that whole song and dance. Right? But we don't. You could just do the adjacent side part. And last but not least, we could prove it's a parallelogram, then show the diagonals are congruent using distance. Right? So again, we're not talking about distance that much. We're not going to worry about that piece. Right? But that is another way that you could prove something's a rectangle. So we've got some snow. I know that as we're moving into spring, we just had that snowstorm, like what, week and a half, 2 weeks ago. Right? Don't really want to think about snow too much, but on this one we're going to talk through it. So what we want to do is prove that this is a rectangle. So what I'm going to do is I'm going to try and prove that all of the adjacent sides are perpendicular to each other. Right, so that means that I want things that are opposite reciprocals. Right, so what I'm thinking is sometimes when I'm doing these types of problems, it's a little bit easier to just kind of go over to the graph and count it out that way and put my slope right next to it. Right? I know this might be a little bit tough if you're working on this stuff like at your home desk or wherever you're working on your schoolwork, right? But you can just kind of keep track of it. Draw out a little sketch. Say I was doing this out on the side and I wanted a little sketch. I would just kind of, freehand a rectangle, figure out what this is, figure it out on my screen, and then just put in like, oh, this is, 18/43 as my slope. Not that that's what ours is going to be, because that sounds awful. Right? So it's not a bad idea. On here, Right, what I'm going to do is I'm going to figure out the slope of each side. So from S to N, right, I'm going 1, 2, 3, 4, 5, 6, 7 up. So my rise is 7. My run is 1, 2, 3, 4, 5, 6, 7. Wow, look at that, 7 and 7. So my slope for that, right, my rise over run, we went up 7 and over 7. 7 over 7 is the same thing as just 1. Right? What we could do is we could treat this as 1 over 1. That's not a bad idea. Oops, a daisy. Don't want to erase the whole thing. Right, so 7 over 7 we're going to treat as 1 over 1 as our slope there. Right, then we're just going to move around the other sides. Right, going from N to O, I'm going to go 1, 2, 3, 4, 5 down. So that's negative 5. 1, 2, 3, 4, 5 over. So negative 5. And then we went over 5. That's the same thing as negative 1 over 1. Right? Because we can reduce that all the way down just like we did with the 7s. Actually, let's leave that 7 over 7 up. Not going to hurt anything. Alright, so this had a slope of positive 1 over 1. This had negative 1 over 1. We'll figure out the other ones real quick. Right? From S to W is 1, 2, 3, 4, 5 down. 1, 2, 3, 4, 5 over. Right, so that matches up with the last one we just did. Negative 5 over 5. The same as negative 1 over 1. And then last but not least, we got woo! W to O. 1, 2, 3, 4, 5, 6, 7 up. 1, 2, 3, 4, 5, 6, 7 over. Right, so up 7, over 7. 7 over 7 is the same thing as 1 over 1. Right? So we've got all these different slopes now. Right? We know that this pair of opposite sides. Right? These ones are parallel because they both have slopes of 1 over 1, right? So we know that those are parallel. We also know that this pair of opposite sides are also parallel because they both have a slope of negative 1 over 1, right? So we kind of, along the way, proved that this is a parallelogram. That's never a bad thing. Right? But now we're worried about is, are the adjacent sides perpendicular? Right? Like, is this side here perpendicular to this side here? Right? And as I'm looking at it, right, I'm taking a look at those slopes, 1 over 1 and negative 1 over 1. If I take, this 1 over 1 and I flip it, if I find the opposite reciprocal, I flip it and change the sign to its opposite, that does give me negative 1 over 1. Right? So these are, in fact, perpendicular to each other. Right? If I go around the whole rest of the shape and try not to erase everything all at the same time, maybe? Oh dear. Never mind. We're going to leave the highlighter there. If I go around the rest of the shape, right, I'm going to find that NO is parallel to OW, right, for the same reasons that we just talked about. OW and WS are also perpendicular. WS and SN are also perpendicular. Right? So because we had opposite reciprocals the whole way around, that means that we can say that snow is a rectangle. Right? So when we get that, mid-May last snowstorm of the season, you can go out and shout at the clouds, be like, "You're a bunch of rectangles! Ah, snow's a rectangle!" Right? Don't do that. Your neighbors might think you're crazy. But, it just happens. Anyway, that's it for this one. Be sure to check on Google Classroom for any additional resources or assignments, and I will see you later.